second of our seminars today, and it's a very great pleasure to have David Aldous joining us, and he's going to talk to us about the critical beta splitting random tree model. David, over to you.
Okay, thank you very much. I'm gonna jump in. Okay. Well, now we practiced this and it's not going. Oh, there we go. Okay. I'm talking about one specific, fairly simple to describe model. Mostly I'm more of a big picture person, so I want some justification of why spend an hour talking about one thing. And well, firstly, there's some weak but cute real-world motivation, which I'll start off with. It's a random tree model, so there are lots of aspects to study. So we actually have both interesting results and open problems. My own interest, as some of you will know, is with the limits and the Brownian continuum random tree. This has a different limit, but one can still ask similar questions about the scaling limit of these finite models, and we haven't done that. I'm sort of leaving that for future work. I came up with this idea as a model to study 25 years ago. I spent 24 of those years occasionally trying to find a smart young person to do the actual work and prove some theorems. I failed in that, but last year I found a smart old person, Boris Pittel, PhD 1963, do the math there. He got very intrigued, and so we now have two long preprints on archive, one by Boris analytically, one by me probabilistically, with part of it which are parallel. A lot of it is doing the same problems by different techniques, and of course there's some history of that in random trees already, but it's just fun to do and kind of encourages one to actually work. A quick digression for people who get bored here. An unrelated problem that intrigues me. Take your favorite complete set probability metric space, take a probability measure, take two samples from that probability measure. There's a distance between those two samples, which has some distribution on zero infinity. What distributions arise in this way? That question could have been asked almost 100 years ago. Questions like this, you think somebody must have thought about it already, and apparently not. And we know a little about some sufficient conditions, some necessary conditions, but we have no idea whatsoever. We have no conjecture for what a necessary and sufficient condition is. So if you like sort of abstract stuff rather than my more concrete stuff, that's an intriguing question. So I'm going to start off with the real world loose motivation. This is a phylogenetic tree, or to be more precise, a cladogram on 77 species of parrots, mostly from the Amazon jungle. This is showing evolutionary relationships. It's based on DNA for living species. If I was talking about sort of the human chimpanzee split, we have lots of fossil evidence about extinct species. Unfortunately, dead parrots in the Amazon don't fossilize very well, so we don't really have a fossil record here. And the interpretation of this is a bit subtle here. There's no absolute time scale being claimed here. So even though my sort of a split here is at the same height in my diagram as one there, we're not asserting they happened at the same time. This is just assertion of relative orders of things that presumably goes back a few million years. But the subtlety is that what's going on is up here is that there's some unknown number of parrot-like species, and of this unknown number of species, one has exactly one living descendant species. Again, this has gone through a bunch of different species, like we've had in the 6 million years between the human chimpanzee split, you've had a bunch of different species there. But anyway, this one long extinct species up here has exactly one descendant. This has 76 descendant species, and all the others have 0 living descendant species. And that's okay, that happens. But the point is this somehow happens recursively most of the time. When we look at these splits, they tend to be very uneven. Mostly a few species have sort of split off from the rest, and of course sometimes we have more even splits. And the issue is kind of what's going on here. This could be some artifact. I mean, these aren't exact, so these are just best fits to data. So there could be some sort of artifact in what you're looking at, but the biologists believe it's more or less true. And you can check this for yourself. You go to Google Images, type in parrot phylogeny or rabbit phylogeny or any phylogeny you like, and you'll get a whole bunch of these pictures. To demonstrate this, having already said dead parrot and something completely different, I'm going to continue the Monty Python theme of thinking of phylogenetic trees. I'm going to, those with an intimate memory of Monty Python episodes will recognize these things. So if you look at brontosauruses, so everybody draws these trees differently. They're just plugging into some computer program with the biology data, but they all can convey the same information here. So Brontosaurus is actually Apatosaurus down here, and we have this sort of very clear idea of sort of a little species or branching off successively here. If we go to swallows, it's a little more even. These splits up here, you're having a large sub-clade. I'm going on to the biology word clades for a subtree at any stage. But when you get down here, we're still seeing this these uneven splits at a lower level. Go on to actual pythons and related snakes here. Again, we're starting here, tree the other way. There was rather relatively small clades are branching off the main line at each stage. So the issue somehow is there a sort of simple probability model that replicates this type of shape of the tree. And way back, I did some sort of very small scale looking at data here, that at each split of each tree, you have some number m of species are splitting into clades of sizes I and m minus I. And so if you look at the smaller size at each stage, you find that the median size of the smaller subtree scales very roughly as m to the half. The point being that if you look at sort of the most simple and well-studied probability models, at least before 2000 when I was doing this, they didn't have this behavior. The splits were either more even, order m, or much more uneven, or constant, or log order. Now, of course, you can always invent models with lots of parameters and fit parameters to data, but those are a very simple model that predicts this specific m to the half as the median size of the smaller subtree. And the answer is you do this by cheating. So a real biology model would be forwards in time, and you end up with a sort of a random size for the number of living species. But we're going to sort of cheat and condition on that. We're going to say what's the model for trees on a given number n of leaves, a given number n of species here. And so one can just artificially do this by specifying a probability distribution on splits. For each m, we just specify some distribution of how a size m tree is going to split into sizes I and m minus I, just symmetric in I and m minus I, and then we just recursively construct a tree by splitting in this particular way. So the simplest way of sort of saying that absolutely in all detail is to think of it as discrete interval splitting. We're thinking of our n species, our n leaves, there's just integers 1 up to n. And so here I started with 20, and my first random split splits 20 into 3 and 17, and then recursively 3 splits into 2 and 1, etc. 17 splits into 1 and 16, and then 16 splits into 4 and 12. We just go on until we get down to singletons. So that's now a sort of a very precisely defined mathematical object, depending on how we specified the split probabilities, then of course, okay, we have to be more explicit about what these split probabilities are. As interval splitting, if we want a distribution on the continuous unit interval, the natural ones are the beta distributions. So the first thing we do is if we get down to a one parameter family, where the chances of n splitting into I and n minus I scales like this, it's sort of interesting for this range of values of beta. When you look at the behavior of this, and the natural first thing to look at is the distribution of the heights of leaves here. You see there's a phase transition at beta equals -1, but if you split more evenly, then the sizes of each level are going down geometrically, so you have log n height. If you split very unevenly, then you get a sort of polynomial growth, but beta's negative here. And we're going to study the critical case, beta equals -1, with two motivations. One is that, as we'll say in a moment, this actually fits m to the half data. I mean, and again, and secondly, it's a general idea that we know from lots of other examples and the physics type things and percolation, that if you have a model which has a phase transition, then sort of what's happening at the critical value is often more mathematically interesting and sort of doable. So as I said, we sort of mentioned this a long time ago as a project worth thinking about, but not done until recently. Just an actual simulation of the model, again, comparing our 77 parrot species with a simulation of the model on 77, and draw it in the same way. And note, of course, that the biology it's natural to look at our trees from the viewpoint of the leaves. So in math modeling, we're more used to thinking about Galton-Watson processes, and we think of a tree relative to the root. Both aspects are interesting. Here's a simulation. It's not a perfect mimic of this particular model. If you actually go back to the three real other cladograms I showed, this is actually more like the snake one, but it has roughly the right effect. And if I actually drew more classical models in the same way, that they'd look for entirely different. So this is actually a better fit than it looks. Okay, that's the biology. What's on the math? To get started, I'm not going to say any math more than very rapidly going through. We have a normalization constant, which fortunately is easy to work out. We get our harmonic numbers, hn, which of course we know is asymptotic to log n, and then it's this little calculation that checks what the median size of the smaller split is. What actually happens at the smaller split is basically n to the u, where u is uniform on 0, 1. So that's why the sort of median is n to the half. Okay. So if I want to, I just showed a picture of the tree from the leaves. What does it look like when we go from the root? There are lots of ways of drawing trees. I sometimes think there's a one-to-one correspondence between interesting theorems about trees and ways of drawing them. What we have here is some sort of a mathematical little tidying up to show the same information. If I look at just at the positions of the leaves here, 20 leaves, I've copied them here and just rescaled to fit. So this is an actual sort of exhibiting the tree structure that isn't so visible here. And now for reasons that become clearer later, because we're going to switch from this discrete step construction to a continuous time construction, we have this sort of non-standard representation here, but it's just a non-standard representation of a binary tree, but where we've drawn with this strange convention that we have leaves sort of attached to the middle of some branches, or leaves appearing as twins, as pairs at the end of a branch. And again, this conveys exactly the same information. We're distinguishing left and right here, so that this conveys exactly the same information as this, but with less ink and in a more convenient way. So in some overview of the results, we start with this discrete time construction. It turns out to be mathematically nicer to embed into continuous time. This sort of maintains all the information as a sort of a jump chain. So we haven't lost anything. We've just sort of added something rather artificial, these split rates. So we're going to think that large clades get split faster than small clades. A basic result, again, is the time at the height of the tree in the picture, the time reached in this time-dependent construction of a random leaf scales as order log n, and we can do by analytic methods, we can get some results by probabilistic methods I'll talk about. One can get much sharper results, sort of amazingly sharp results, to my mind, by analytical methods. So the story, I don't want to make too many humorous comments about my co-author as an analyst, but his reaction is to my results is Euler and Lagrange could have done this much better, and he kind of basically demonstrates that in his preprint. So again, we can another result is we can describe the sort of fringe distribution in the n to infinity limit. What makes this mathematically interesting is that there's a non-obvious consistency property in continuous time. It doesn't happen in discrete time. You know, these constructions are separate for n and n plus 1, because we're sort of, it's like conditioning a Galton-Watson tree on having a total progeny n. There's no natural connection between n and n plus 1. The same here. But there is a sort of an actual non-obvious consistency property, which I'll talk about first. And again, there's a scaling limit here that, you know, if we go back to our interval splitting representation, then, well, I could split the continuous unit interval, and I could split it according to the beta equals -1 distribution. And that makes sense, except that we have sigma finite measures. So actually dealing with the rigorous details is a bit messy, and I'm wanting to find some smart young person to think about that. But again, as with sort of Galton-Watson trees and the Brownian continuum random tree limit, you know, you have discrete trees are embedded in the limit as sort of spanning trees on random points, and the same is happening in this model. Okay, so our trick, of course, is that in discrete time we split with these probabilities, because probabilities have to add up to 1. In continuous time, you know, the transition rates don't have to add up to 1, so we can just sort of multiply by hm-1 to make the continuous time chain, and that goes away, and we get this more friendly looking split rate. What does the tree look like in continuous time? It looks very odd. We're going to be starting down here. The first splits happen quickly. What's happening down here is that the kind of final terminal branches to a leaf pair, you don't see the leaf pair here. These have exponential 1 distribution, but here n is 400. There are several hundred of these, and we see the long ones, which look odd. Of course, you don't really see the many hundreds of small ones that are kind of embedded in the noise down here. So it's a non-standard and sort of weird looking and not biologically very interpretable or realistic. But again, it makes it interesting as math, just because it is different from other random tree models. So let me spend some time on this consistency property, which has really got me interested in working seriously here. That our representation with the sort of branches and side leaves and end leaves gives us a natural way of making sense of the kind of connection going downwards, that if I have a tree on n+1, I can just do the obvious thing of deleting a uniform random leaf. And if that gives me an edge that only has one leaf, I then just prune that back to where it joins the rest of the tree. And very non-obviously to me, this sort of gives us the relation between n+1 and n. Roughly where it works, how it works is the following, and it's a little counterintuitive. So I want you to think about the n=400 big tree I just showed you, and now thinking of picking 10 random leaves from those and just looking at the spanning subtree on the 10 random leaves of this bigger tree. And then I do my prune operation. I take every leaf of this and prune it back to where it joined the rest of the tree. And I now get something I can write in my odd standardized form. Now, the counterintuitive point of this is that if I had n=400 million instead of 400 and did the same thing on k=10 leaves, these end bits would be much larger because they're going up toward a log of 400 million. But the branch points stay the same, the order of magnitude. So I still get a picture that looks qualitatively like this as n goes to infinity. And the reason is that a simple 1 or 2 line calculation shows that sort of within our model on n, that the time at which the paths to 2 different random leaves diverge, that is the height of the branch point, just has exactly the exponential one, a distribution. It's a somewhat magic but mathematically trivial fact to check. So if this is true for k=2, then it's true for every fixed k. There has to be some limit here, as I just said, that I take k=10, and there's just a limit as n goes to infinity distribution when I take this embedded tree, but then prune back to have a tree looking like that. And moreover, if this is true for every k, then the relation between k and k+1 is exactly a sort of delete and prune thing, just because that's the relationship between k+1 random leaves and k random leaves. So you just get k random leaves by deleting one of the k+1. So somehow it's intuitively obvious that the limits here have our consistency property, and then the issue is, well, is the limit actually the same as our model on k? And that isn't obvious, but of course both have to have this property star, and it's sort of kind of inconceivable that 2 different models would both have this same strange property. So they have to be the same morally. And there's a kind of abstract but strangely unconvincing proof, because it's Bayes with improper priors. We probably know that in Bayes' world, I'm doing inference on normal mu sigma squared. So take mu uniform on 0 minus infinity to plus infinity, take sigma scale invariant on the path line to do your data, and the posterior is fine. So there's this argument, but somehow I don't want to submit to Annals of Probability a paper that does that. So unconvincing proofs here. But one can also do it bare hands by just writing down the down exactly the sort of microscopic description. What's the probability of a given tree shape and different things? And you end up then with this sort of explicit but non-intuitive. I mean, you get it. So we get this sort of simple rule for going upwards from k to k+1, but it's not something one would ever guess without doing the calculation. And it says that. I'll do this on a picture here. So here's my tree on 10 leaves. I want to show where to put an extra leaf. So I'm picking a random existing leaf, this one. So one option is that my new leaf is going to be a side leaf here, and that goes by the rule that I'm sort of walking up the tree towards my target leaf, but there's a sort of a killing probability, a probability that I'm going to put this which depends on the size of the sort of subtree under where I am. So this starts off with at here there are sort of all 10 existing leaves. So I'm being killed at rate 1/10. Here there are sort of 9 remaining leaves. When I get here, I've got 6 remaining leaves. I'm being killed at rate 1/6. Here I'm being killed at rate 1/5. And now this killing event happens, and I am putting my new leaf there. If the killing event didn't happen, then I get all the way up to this leaf. And now the rule is that I expand that leaf, so the other leaf stays where it is, but I'm adding another exponential one length, and then this leaf and my new leaf get there. And the final possibility is that, again, the leaf I chose was this side leaf, and if I get there, then I'm expanding my side leaf. I can't see this on my side. I hope you can see it into a branch, again, with exponential one length. So again, that's the construction. So I was very pleased when I figured this out, because I said, okay, we now have this inductive construction. We can think about almost sure limits. We can do anything. And unfortunately, I can't actually do anything with this. So this reminds me of things like Earn models or branching random walks, where there are interesting martingales you can use. So my intuition is that there's some interesting martingale that one can sort of associate with this process, but I can't find it. So there we are, more things to think about. Okay, so what have we actually done? So the simplest thing, as we mentioned before, is to think of the height of a random leaf, that is the time at which our continuous time construction gets there in our continuous time model. This turns out to be something simple, that as we go along the route, at each point there's a sort of subclade relative of all the leaves above where we are. And the size of this of this process, I don't have a good name for it, the explorer chain, because I had to say something, turns out to be this very simple to describe continuous time Markov chain on integers. We're starting at n, we end up at 1, we end up, when we get to a leaf, we stop at 1, and it just has these rates. You're going downwards, you jump a distance, you jump a certain distance down with probability at rate 1 over the distance. So I figured this out 25 years ago, but in the strange way that research works, you say, someone must have thought about this chain before. People have been doing Markov chains for 100 years, and I don't really want to sweat away proving things that probably someone's proved before. So again, we haven't actually discovered anyone proving it before, and in particular, since Boris can prove much sharper results than anyone else can prove, we're not too worried about that. Let me do I'm going to throw in a simple calculation here that leads up to a mention of the analytic techniques. Somewhat unexpectedly, for this particular chain, we can get an exact formula for the expectation of xt. That's because I'm jumping a distance I minus j with chance 1 over, with rate 1 over j minus I, and we're summing 1, and that's the sum I can do. It turns out by here that we get our expectation of xt has this explicit formula. Again, it decreases from n to 1 as time goes on. And by Markov's inequality, again, we're looking at the dn as the time until this chain reaches 1, we get this explicit inequality for it. Now, this is interesting for several reasons. That if one somehow guessed this, or if one, like my co-author Boris, thinks this calculation is nonsense, one can check it by a recurrence. So back to very elementary Markov chain theory, you have recurrences for expectations here. So there's a recurrence, so that dn is just, we have our rate as of time until something happens is 1 over this, and then we look at the probabilities. So this is just very elementary recurrence. To prove analytically the inequality I just stated, it requires sort of guessing what the answer is. So if we magically guess that expectation is less than this explicit, if we guess that this unknown quantity is smaller than this known quantity, then to check that kind of inductively, etc., we just have to check that fn's satisfy the inequality associated with this equality the right way round, which is this way round. And then sort of checking something like this particular fn turns out to be one long line of calculation. So again, we don't need to read through this, but just to take it on faith, you can just sort of check this by basically Jensen's inequality somewhere here. Okay, so to this audience, at least the probability half of this audience, the sort of probabilistic argument seems more natural than the recurrence argument, but somehow it was pure luck that we can do this particular calculation in this particular case. And the point of the recurrence argument is that anytime you could guess an explicit bound, you have this sort of mechanical process of trying to verifying it. And in fact, preprint number 1, which is basically written by Boris, is a long paper doing sort of the using this particular type of technique to get surprisingly sharp results purely analytically. So what's going on here, back to the probabilistic sense, is that our chain is decreasing in a multiplicative way. A good sort of first course exercise, open-ended exercise for students is to say, what can you say about the product of the partial products of IID uniform random variables? Because of course the first thing you can say is its expectation is 2 to the minus n, but you then realize that the natural thing to do is to take logs, and you can apply the strong law of large numbers and central limit theorem to the log process, and mn goes as e to the minus n rather than as 2 to the minus n. And so exactly the same is happening here. Again, we have this continuous time chain with these rates, but inspired by the last example, we say, let's think of the log of that, and let's think of what a transition for the log process. Again, it's decreasing, so you go from z to z minus a, and a little calculation here says that the rate of transitions from z into the interval sort of below z minus a is approximately this particular number, which just depends on a. So we're having a sort of Markov process on the line where the way it moves doesn't depend on where you are. That's a random walk, a continuous time analog of a random walk. And more technically, it's a subordinator, which is again the monotone random walk where you're allowed a lot of small jumps as long as they don't add up to too much here. So there's this very specific subordinator, or YT, you can define, associated with this particular measure, the way it evolves. We have this intuitive approximation that our xn starts at n and ends up at 1, log xn starts at log n and ends up at 0. And until it gets close to 0, it's going as log n minus this subordinator. And again, we're studying the time until the log process hits 0. And subordinators are just like partial sums of IID things. You have a strong law of large numbers and central limit theorem. Strong law of large numbers involves, the expectation is the mean, and the mean is the integral of this function, which by one's own ability, limited in my case to do calculus or looking up, is a classic identity that this is theta 2 pi squared over 6. So that's the speed at which we go from log n to 0. So the time it takes us then is 1 over the speed. And so we get this sort of the heuristically, we get the sort of correct first order asymptotics. The expectation is 6 over pi squared log n. And similarly, if we think our approximation is good enough to apply the central limit theorem, we get a central limit theorem and another integration exercise allows us to work out the variance in the limit, which surprisingly or not, it involves theta 3. So actually doing this, rather than waving your hands, my ability to do this is kind of a horrible hack. It takes a few pages, and it's just sort of messy to justify the approximation. Of course, if you're Boris, you sort of don't believe in subordinators or anything like that. But so he said, look, you can have a recursion for expectation. You have a recursion for variance. You have a recursion for Laplace transforms. So Euler and Lagrange or Laplace. I'm getting confused with my historic history here. I think Euler and Laplace knew how to analyze these recursions. So you can actually do it, and because it's a good check to prove by different methods. Again, it kind of depends on knowing the answer, of course. So somehow I told Boris this is the limit, and he said, "Oh, I can prove this better." But it's also technically intricate. I mean, you still have details of approximation. So I'd seriously like a sort of clean probabilistic proof of this. Again, remembering this isn't any sort of general theorem with sort of under these hypotheses. It's this very explicit, simple described Markov chain. So there has to be some clean way of doing it. Just for fun, there are books on pi e 0, 1, 2, 3. You may not know there's a book on theta 3, but there you are. There's a book on theta 3, claimed to be the world's most mysterious unsolved problem, but I don't quite think that's an accurate thing. But anyway, just for fun here. Anyway, so I'm going to say a little about what Boris can do via analytical methods. We have this recursion. So purely this recursion, probability gives us the first order term, times 1 plus little o1. There's actually just an additive error rigorously here. Moreover, what gets to be interesting is that if you assume there actually is a series expansion in powers of 1 over n, then by some analytical magic I don't actually understand, you can figure out what the coefficient of n to the minus 1 is without knowing the value of the constant here. Now, actually calculating this numerically, of course, is trivial. It's a linear thing. My kindergarten level Python enables me to do this. And if you run it on my laptop overnight, we can work this up to 400,000. And amazingly enough, because we know this constant, this allows us to actually get 10 significant digits of this.
Sorry, what is H ansatz? What is H ansatz?
It basically is the assertion that there exists a series expansion in 1 over n. Whatever that means. Yeah, I don't have a clearer thing. This is all analogous to the expansion of the harmonic numbers, Hn, where we sort of know such an expansion exists and are using it. Yeah. So it's there. Yeah. So again, one can, and this is weird if, like me, you're used to doing sort of Monte Carlo estimates of expectations, where you run a million simulations. If you're lucky, you get 3 significant digits. But so that's fun. What do Boris's proofs look like? Well, it's getting sharp asymptotics for explicit sums, because again, we can write down everything kind of explicitly. So this is sort of a typical thing you have to prove, and you're just getting very sharp estimates here. This is sort of something depends on n, and you really want to show it has this. You can show what it is up to a very sharp thing, and then the way you prove this, I mean, we know that sums can be approximated by integrals, and we're used to doing that, and there are just these sort of very sharp ways of saying how close a sum is to an integral, and again, going back to Euler, as Boris said here. And again, I don't claim to understand this very well. Just for fun, Hardy, in a mathematician's apology, writing out Ramanujan, said, well, Ramanujan was great, but the age of great formulas is past. But we all still hope to find occasional great formulas. So another thing one can do is, we have two levels of randomness here. We're taking a realization of a random tree, and then we're picking a random leaf in there. And so by sort of analysis of variance, the law of total variance, one can split up the total variance into these two parts, what statisticians would call within tree variability and between tree variability. And then you can ask sort of what's the relative contribution of these two things. And as a standard argument, the relative contribution just comes down to the correlation between the heights of two random trees from the same realization. And again, you can analyze this in the same way. In the limit correlation, the limit proportion, we have this nice formula that, as well as theta 2 and theta 3, involves Euler's constant. So does this matter? No. Is it cute? Well, yes. But going back to methodology, this all depends on sort of assuming you have these very fine exact sort of expansions, exact estimates. And of course, what's really going on here is that we have a bivariate Gaussian limit for the two different things coming up here, the sort of average, the average leaf height within a given realization, etc. We know one of these is Gaussian. We could probably easily prove separately they're Gaussian. So somehow there's a bivariate Gaussian limit for which this is the correlation, and this comes out of some integral. And again, it would be nice to have probability proofs of this which don't rely on these sort of absurdly sharp estimates. Just to give a simple open problem, the height of the tree itself, that is the maximum leaf height in a realization, is interesting in the sense that your first thought that, well, the distributions, we know the limit distribution is Gaussian, so I take the maximum of n Gaussians. That doesn't work because of the sort of weirdness. It actually works in the discrete time construction, but not in continuous time construction, because we have all these sort of exponential one terminal edges, and their contribution is somehow the same order of magnitude here. So we have guesses as to, again, the height is some constant times log n intuitively. We have guesses what the constant is, but it's sort of a kind of non-standard large deviation exercise to prove it. So let's see, going back to my previous slide, I said there are lots of problems to think about. I haven't said much of them, so I'll briefly end up with the fringe distributions and scaling limits with a few more slides. So the issue is that our explorer chain, the simple explicit chain we've talked about, somehow intuitively clear we can sort of start from infinity. So more technically, if I start from n and think about what's the chance it ever hits state I, intuitively we can let n go to infinity and take a limit, and we can actually do this probabilistically by a coupling argument. So these limits exist, except that coupling doesn't give you any useful quantitative information. So analytically, you can write down a system of equations, but of course, this is an infinite sequence of equations, and A3 involves A4, A5, A6, etc. So you sort of can't solve them recursively. So the limits, of course, have to satisfy their own sort of, again, the obvious relationship between these things. But again, we don't actually have a proof that these equations have unique solutions or anything. But if we given the existence of these limits, but again, which we can numerically estimate by simply calculating exactly for a large n, so we know what they are, and we actually also, because we know the speed of log xt, this tells us the kind of Cesaro, an averaged version. So we actually do rigorously know an average version of these limits, and then you can sort of undo that, the sort of canonical sequence that satisfies this. You can say how it goes, and it's going this particular way, which of course is consistent with the numerical calculations we do. But this is where's this going? So what we believe is that, again, if I start off with a leaf of the tree and then say, well, what's the size of the clade it first joins with, W, this is scaling in this particular way, which we recognize as having infinite expectation. So again, we're looking at, a typical leaf, and sometimes it joins 1, sometimes it joins with 2 or 3, and then of course occasionally down here it's joining with a large clade. So one standard thing to do with random tree models is try and code them as random walk-like objects, and intuitively there's some way of coding this as a random walk-like object, but it's a sort of random walk with some infinite expectations. That's what this calculation is saying. So there's something like, I have no idea what a reflected Cauchy random walk is, but if there was a reflected Cauchy random walk, then that would be a candidate for here. So again, we don't know that there's something going on here, and I certainly don't understand it, but it would be nice if there was a random walk description of this limit here. And the other thing I mentioned before is that the scaling limit, so again, that's the sort of local weak limit, the fringe limit. There's a scaling limit, which is just splitting the continuous interval, again, but via this sort of sigma finite way. And again, that's clearly one can think rigorously about it. There are these two separate relevant bits of literature, sort of applied probability literature, which works with sort of more even splits. An old paper of Victorette, for instance. And then there's the sort of exchange, the more general abstract exchangeability approach to these types of coalescence and fragmentation processes. And there's this long paper which is doing something I can't quite relate to what we're doing. And again, it would be an interesting project to connect what we're doing to what's in this old paper. So again, I can't draw a good picture of the scaling limit. You kind of just have to imagine this process done in continuous time rather than discrete time. And again, these analogs and differences here. Okay, I'm going to stop there. Thank you for your attention.
Thank you very much. Does anybody have any questions?
Sorry, you told us the first estimate of time isn't good. In what sense it isn't good? First one, and just at the beginning.
It's good in the fit to data, just in a visual sense. Purely, it looks good. Looks good to me. Yeah. Yeah, I guess I really should show pictures, create pictures of the other graph models and demonstrate my assertion that they look entirely different. I haven't done that.
Thank you.
Okay.
Anybody else?
So on the maximum height question, is somehow the difficulty maybe guessing what the answer should be? Because I suppose there's a distributional recurrence, and is it conceivable if you could guess the right thing, it would prove itself in a simple way just by considering the first split or something like
that? There isn't a very usable recurrence. I mean, you're right. I mean, there is a recurrence for
not for one single thing.
The recurrence involves the whole distribution
family,
rather than one statistic rather than just expectation or variance.
Yeah.
So that's the problem. And then the issue is that it involves there's the sort of correlations between trees as a function of distance between them in this interval splitting thing. So we know about, we understand this correlation between the heights of two random leaves, but we don't understand so well the correlation between the things that are sort of a order n to the alpha apart in the interval. And it kind of comes down to sort of, we can't treat all n leaves as if they were independent normals, because there's obvious local dependence. But the question is whether you can, whether if we look at the heights of n to the 0.27, which I think is little, or right, if we look at n to the 0.27 leaves, it's the maximum of those, like it would be if they were independent. Yeah, so it gets to sort of weird non-standard questions. Yeah, but we actually we do have a conjecture for what it is, but no attempts to prove it.
Okay. Is a conjecture easy to describe, or is it?
Yes, I've just forgotten. I'll maybe try. If it's not written down, yeah, no, it's just something in terms of the mu and sigma, but sort of not so obviously. It requires a bit to explain, but it ends up simple, but it doesn't have such a simple explanation of where it comes from. Yes, so it's something, and it's written it's in the preprint, but so you can look it up. But yeah, okay.
Any further questions from anybody? I can't see anybody volunteering, so what I'm going to do is I'm going to pause